Okay, right. So this week we have mostly um, about numerical methods for integration, numerical methods for yes, yes. I mean that's true. If the class timings are changed, then maybe that may be the case. But we are going to upload all the videos, right? We're going to upload the video, and they can of course follow the video later on. No, no, no. I cannot join them. Like I do not know. There's no way I can join. They have to join me. The announcement from NPTEL has already gone out. But as I said, the announcement was late. Yeah, but I don't. There's no request to join, right? It's the same. If they join the meeting link, then they can join it right away. Yeah, yeah, there's no such thing. Once you join the link, you immediately join the meeting. I do not have to let anyone in. The meeting settings are like that only. All right, let's start. Um, so there are a couple of techniques that I'm going to talk about. For first is for solving roots of uh, systems, roots of equations. Start. Um, okay, so right. I mean, uh, there isn't too much conceptual stuff over here. It's mostly calculations. I'll show you how to perform the calculations, and we can kind of leave it at that. So the first method is the so-called bisection method. And so, what is the bisection method? Let me quickly uh, describe that. Okay, so if you have so here you're given a an equation, fx equals to 0. And for the bisection method, it is enough that that the function is actually going to be continuous. Okay. Now, if you can, um, well, I mean, if you can find out the so what? Okay, so let us quickly describe what it is. So let's say the function looks like this, and let's say this point is A and this point is B. Okay, so let's say you have estimated. So um, all these iterative methods. The idea is to compute a root. That's the goal. But the way this is achieved is that we start off with an initial estimate of the root, and then we progressively keep on improving that estimate. So let me just write it down. Start with an estimate, and progressively improve the estimate. So let me first describe what a general pattern here looks like. So let's say your initial estimate, what you want is you want to compute a root. So you want to compute an x star such that f of x star is equal to 0. This is the objective. You start off with some initial estimate of the root. So let's say your initial estimate is x naught, and x naught lies between a and b. Now the general schema is basically like this. From x naught, you compute, and this is basically the algorithm for computing the subsequent estimates. So any such numerical method, what it is that it's an algorithm, um, and that algorithm basically would take in this function f, and it would take in some estimate xn, and then it would churn out the new estimate xn plus 1. Okay. Um, Now the question is the estimate xn plus 1 uh, always better than the estimate xn? So the question is xn plus 1 always uh, better than xn? And what do I mean by better? So let me put that in quotes. So by better, what I mean is that, so um, uh, uh, you're trying to solve an equation, and what you want is that you want the number to be as close as possible to zero. So a solution would be something which gives the zero, but an estimate is a number which is close to zero. So let's say you compute f of xn and you compute f of xn plus 1. Okay, now you want this to be as close as possible to zero. So now the question is mod of f of xn and mod of f of xn plus 1, if we take the absolute values of this, is it necessarily true that that the mod of f of xn plus 1 is always going to be smaller than f of xn? Uh, is the question. So what we want is that uh, uh, ideally what we want uh, is something like this. We want something like f of x0 mod to be greater than or equal to f of x1 mod, and eventually as the number of iterations increases, what we want is this number f of x of n should be as close as possible to zero. So it should become smaller than epsilon for any choice of epsilon. Okay, where epsilon is like a small number. But the question is, but whether between any two progressive numbers, xn and xn plus 1, the question is xn plus 1 a better estimate of xn? That depends upon the algorithm. There are some algorithms, uh, by algorithms I mean there are some numerical methods for which this monotonicity property would be followed, and there may be some for which it is not followed. Okay. However, what is important a for a root finding system like this to actually work is that um, is basically this. Let me write it down. Uh, this is convergence to the root. Okay. Uh, I'm explaining the theory a little bit over here. The ultimately doing the calculations is actually pretty easy. They're actually straightforward once you just know the method. Okay. So what we want is any such numerical scheme must converge to the root. And what this means is that, so what is the numerical scheme? So you can kind of draw this numerical scheme as like um, as this sort of a black box, which uh, where if you feed in the estimate xn and this function f, it will basically churn out another estimate xn plus 1. Okay. So for the sake of uh, so for the sake of explaining this, so let us call this 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 box. Let's call this as some phi of f. So phi of f is basically like a mapping uh, where phi of f of xn is equal to xn plus 1. Now you want a sort of convergence to the root, which means that, and this is like any other Cauchy convergence criterion, which means that for any epsilon greater than 0, there must exist an n such that for all n greater than n, f of xn mod should be less than epsilon. All right. So with this sort of framework that we have, let us first look at the first method, which is called the bisection method. Um, so the bisection method basically works like this. So let's say you have a function fx, and let's say you have an interval within which you know that a root must exist. Okay. So of course, f is a continuous function. So that is equivalent to saying that fa times fb is less than 0. Okay. You are assuming here that there is a single root between a and b and not like multiple roots. Okay, because if there are multiple routes, then again the choice of the initial estimate will determine which route you converge to. So we'll look at that later, but let's first look at this example. So you start off with any estimate of the route. Okay, so let's say you start your estimate x0 as it could be any point between A and B. So it could be anything between A and B. So let's say you choose your x naught to be equal to, let's say, A plus B by 2. Okay. So let's say somewhere over here, your let's say your x naught lies. Okay. So now you have to basically estimate on which side the root lies. Okay. So so the idea is basically this: determine. So let's say you call your root as x star. So determine whether x star lies in a comma x naught, or whether x star lies in x naught comma b. I mean, if x naught is equal to x, if x naught is equal to x star, that is, you have found the root, then you basically stop. There's nothing more to do. And how do you determine whether H star lies in this or this? Well, you just apply the check. So, so this is basically equivalent to saying that f of a times f of x naught is less than 0. And this is equivalent to saying that f of b times f of x naught is less than 0. Okay. Either one of these conditions would be true. Both cannot be true. So depending on which condition is true, you you take a subsequent estimate. So let me just write it over here. We define, let's say, two conditions. Let's say C1. So C1 is basically this, that uh, f of a times f of xn is less than 0, and C2 is f of b times f of xn is less than 0. So the algorithm is this: if C1 is true, then you set your xn plus 1 to be equal to a plus xn by 2, else you set xn plus 1 to be equal to xn plus b by 2. Okay, and then you keep on repeating this procedure until, of course, uh, you might have to continue this procedure ad infinitum. But so let us just write what is the stopping criterion. So what is the stopping criterion? So the stopping criterion will generally be given to you, is generally going to be some number epsilon, which is going to be like a small number, and you stop whenever f of xn is smaller than epsilon. Okay. So for example, they may say estimate the root. I Okay. So for instance, they may say estimate the root up to 3 decimal places. So if they say estimate the root up to 3 decimal places, what this means is that your epsilon is basically equal to 10 to the power minus 3. Okay. So whenever this is satisfied, you basically stop this iteration, uh, and you report your whatever xn that you get. You report this xn as your root essentially. Okay. All right. So I hope this is clear. This is a pretty straightforward procedure. So let's solve this. Again, I'm not going to do the calculations here. It's just going to take up a lot of time, which is just not necessary. But what you can do over here is that you have this cubic equation: f of x is equal to x cubed minus fx minus 5x plus 1. Um, so let's say you start off with like an initial estimate of the root. Okay. So let's say you start off with, let's say, a point 0 comma 1. You look at the interval, let's say 0 comma 1. So at 0, this is equal to 1, and at 1, this is equal to minus 3. Okay. Also, let us compute f dash x. F dash x is equal to 3x squared minus 5. And of course, what you notice is that within the interval 0, comma 1, of course, the f dash x is negative in 0, comma 1. So what this basically guarantees is that there exists a single root in 0, comma 1. That means that there exists a single root in 0, comma 1. So for this bisection method to actually work, you require that in the interval within which you are performing this estimate, there is a single root. Because if there are because if there are multiple roots, then it's possible that it converges to one root or the other root. Okay. Um, so here, of course, there exists a single root because the function is decreasing. So the function looks like this. It is positive at 0 and negative at 1, and f dash x is negative, which means that it is a decreasing function. So there exists a single root only. This is not a necessary condition. This is a sufficient condition. So as long as f dash x does not change sign within within a particular interval, there can be at most one root within that interval. Okay. So here, of course, f dash x does not change sign. It is always less than 0. So now you can start your estimate. Um, so let's say you choose your x naught as equal to um, half, and then you compute your f of x naught. Your f of x naught comes out to be equal to something like minus 1.37. Now you have to make a decision whether like basically you have to check this condition C1 or C2. If you check f of 0 times f of half, you will see that this is negative. So your C1 is satisfied, and you choose your x1 to be equal to 1 by 4. All right. And again, you perform the computation. So you get f of x1 to be equal to something like minus 0.23. Right. Next, what you do is again, so this is the first step of the iteration. This is the second step. Again, in the third step, you have to check these conditions. So again, you will see that f0 times f1 by 4 is negative. So this time you choose your x2 to be equal to 1 by 8. And you'll get this f of x2 to be something like 0.37. So one thing that you can sort of notice is that um, is that from 2 to 3, as we go from 2 to 3, the estimate did not become better in the sense that f of x1, if you take the absolute value of f of x1, that is actually smaller than the absolute value of f of x2. Okay, so so as like a rule of thumb, when you perform this iteration for a few times, then you can get this sort of oscillation. But eventually, somewhere close to the uh, root, uh, you can uh, you can sort of guarantee that. As you get closer and closer, your estimates, well, I mean, the estimates can keep on varying, to be honest, and this is one of the drawbacks of this bisection method. Um, right. I mean, the reason why the this method is, despite being a simple method, is not such a um, not such a useful method, is because the estimate that you are making, the estimate can jump around the root, so it can sort of oscillate from this side of the root to the other side. And what it does not give us is that it does not guarantee that you will get progressively better estimates as you perform this iteration. So when to stop the iteration can become challenging. Okay, because you do not have any such monotonicity property that you are getting better estimates each time. Anyway, so right, you perform this computation a few more times, uh, and then you check. So you can do this computation a few more times, let's say up to iteration 4 or iteration 5, and then you check which of this actually gives you the closest to the root, and whatever that is, then you choose one of those to be the answer. But like whichever is closest to the option, that is the answer. Okay, so I hope this is clear. Okay, let's proceed. Just give me 1 second. Okay. I mean, let us give like a small proof why this thing works. This is quite easy to see. Um, so essentially, what is happening is that um, you have an interval a b, and let's say your function has a root over here x star, and what this algorithm or what this procedure always does is that uh, within this interval a b, from this interval a b, it chooses another interval. The first such interval is okay. So the first interval over here is some I0. Let's call that I0 is AB. Then it chooses another interval I1. Okay, and the interval I1 that it chooses, uh, so your x naught over here is a plus b by 2. Let's say this is your starting estimate. So the interval I1 that it chooses also contains the root x naught, sorry, x star, and the interval I1 is is half of the interval I0. So the length of the interval I1 is half times the length of the interval I0. And I1 also contains x star. Okay, because that's how we basically choose. So let's say if this was your x naught somewhere over here, we go either to the right or to the left based on that condition C1 and C2. So effectively, what we have done is that we reduce the search space to to a smaller interval I1, where this interval I1 is smaller than is half times the length of the interval I2. And similarly, this procedure continues. So at the nth stage, we have an interval in, which continues to have this root x star, and in is the length of in is half times the length of in minus 1. Okay, so what you basically have is that you now have this chain of intervals, um, each containing x star, and of course the length of each of these intervals uh, decreases, and so um, what happens is that at as n tends to infinity, uh, xn tends to x star. Okay. Okay. So yeah. So I hope the convergence is clear. Why this method converges to the root x star. This is the small proof of convergence. Okay. Now let's look at the second such root finding method. Okay. So the second such root finding method is the Newton-Raphson method. Um, and What this basically says is this is how you this is basically the iterative scheme. So you have xn plus 1 is equal to xn minus f of xn by f dash of xn. Okay, so immediately you notice that for the Newton-Raphson method to work, you require the equation to have at least one derivative. Otherwise, it will not work. Okay, just give me one moment. I'll be back in one moment. Okay. Um, right. So let me draw a picture first. So let's say as before, this is your function, and you have a root here at x star, and you have some estimate of the root which is at uh, xn, let's say. Now the idea is basically as follows: uh, you draw a tangent to the curve at this point, which is xn comma f of xn, and wherever this tangent actually intersects, we call that xn plus one. Okay, what is the equation of this tangent? Well, the equation of the tangent at xn. Uh, so if you consider the tangent at xn as this point xn comma f of xn, then the equation of the tangent is basically y minus f of xn is equal to f dash of xn x minus xn. Now, where it basically intersects the x-axis, you have x to be equal to, this is the place where it intersects, the point where it intersects the x-axis, that is given by xn minus f of xn by f dash of x. Okay, and uh, it's kind of clear now that when you have this sort of uh, going on, then this xn plus 1 is now significantly closer to the root. And this is basically how the iteration proceeds. Uh, the advantage of the Newton-Raphson uh, is that it has certain limitations, but those limitations basically are sufficient conditions which tell you when this method will indeed converge to the root. But when those conditions are met, then the Newton-Raphson method is actually quite faster than the bisection method. The convergence is much more rapid. So let us solve this example only. Okay. So here they've essentially given you what the initial guess is. The initial guess is 4.2. Um, it's also easier um, to carry out the Newton-Raphson method. Um, just give me 1 second. So what is f dash x here? So f dash x is equal to 3x squared minus 46x plus 135. So the iteration scheme is basically this: xn plus 1 is equal to xn minus f of xn by f dash of xn. This is equal to xn minus um, xn cubed minus 23 xn squared plus 135 xn minus 225 upon 3xn squared minus 46xn plus 135. Okay. Um, and now it's just performing the computations one after the other. Okay. Um, I leave it to you to perform these computations. You can complete the calculation and pick one of the answers from here. Okay. This is fairly straightforward. uh, okay. So I think okay. There's one more method. Let's look at that. But before proceeding, I wanted to uh, maybe discuss one more problem. Just give me one moment. Let's also consider. Okay, so another way of or another way in which we can find the root of an equation. So let's say you have an equation of the form f of x is equal to x. Okay, so let's say this is an equation. Okay, uh, so then one says that uh, any x star that satisfies f of x star is equal to x star is called a fixed point of f. Now, the thing is that there are many equations which can be which can be sort of recast to uh, to ask to basically solve for a fixed point. So let's take an example. Let's say you have a cubic equation of the form some x cubed plus 1 minus x equals to 0. Okay, you can write this as x cubed plus 1 is equal to x. Okay, where f of x is equal to x cubed plus 1. So effectively, you can, when you have an equation like this, you can recast this equation to basically say compute a fixed point for f. Okay. Now these fixed point theorems in calculus, this is just like a aside. Fixed point theorems in calculus are very popular, and there are many fixed point uh, results, from very simple fixed point results to very advanced fixed point results. But here we're going to look at a very uh, we're going to look at a very simple fixed point result, which we get if this function f satisfies what we called a contraction principle. This contraction principle. So what this means, we say, so let's say there is a function f from some open subset uh, u to r. You can assume for now that this open subset is an open subset of R, but it can be an open subset of Rn also. Um, and it need not be just over R, it could be in Rn. But we say that this F is a contraction mapping. F is a contraction mapping if for any x and y in this domain U, f of x minus f of y is less than or equal to c times the difference between x and y. Okay, where this constant c must, of course, it's a positive constant, where this constant c must explicitly be smaller than 1. Okay, um, so uh, if this property is satisfied, okay, that is if f is a contraction mapping, then we have one of the most fundamental fixed point results, which is called the Banach fixed point theorem. It says that if f is a uh, if f is a contraction map, f is a contraction, then it has a unique fixed point. Okay, so let us see like a quick proof. So first proof is the proof of is the proof of existence. The proof of existence is as follows. You start off with any number x0 and you compute x1 to be equal to f of x0. Okay. In short, you compute xn plus 1 to be equal to f of xn. That is, you basically you starting off with any initial number x0. You have computed a sequence of numbers xn. Okay, and the claim is that limit n tending to infinity xn, uh, this limit exists. If we call this limit as x star, then x star is a fixed point. And why is that? Well, notice that xn plus 1 minus xn mod is equal to f of xn minus f of xn minus 1 mod, which is less than or equal to c times xn minus xn minus 1. Okay, and therefore, what you get over here is that uh, x of, and you can sort of repeat this process. So you get x of n plus r minus minus x of n plus r minus 1 is less than or equal to c raised to the power r xn minus xn minus 1. In general, you get this xn minus xn minus 1 is less than or equal to something like c to the power n x1 minus x2. And so basically what you get over here is that this sequence, the sequence xn is a convergence sequence. Just give me one moment. Right, so of course, the sequence is a convergence sequence, and let's say limit of the sequence is equal to um, x star. Then of course, um, x star is a fixed point. So x star is equal to f of x star. Okay, um, and why is this unique? Because let's say if you have two fixed points, then f of x minus f of y is less than or equal to c times x minus y. But f of x is equal to x only because it's a fixed point, and f of y is equal to y because it's also a fixed point. You get x minus y is less than or equal to c times x minus y, which is obviously a contradiction. Okay, so this contraction principle is something we're going to use in finding roots. So let's see how. So now let us bring us back if we have a function from R to R. So say f is a map from an interval a comma b to R, and uh, assume that f has first order as um as uh, yeah. So say f is c1. So now of course we know this um, from the mean value theorem that if you give me any points x1 comma x2 that lie in a comma b, then f of x1 minus f of x2 by x1 minus x2 is equal to some f dash of x, some number theta, where theta lies between x1 and x2. Okay, um, so that you get f of x1 minus f of x2 norm is equal to f dash theta norm times x1 minus x2. Now, if so, a sufficient condition for this to be a contraction map, so let me just write it down. A sufficient condition for this to be a contraction is that f dash x norm is always smaller than 1 for all x in a comma b. Okay, so if this criterion is satisfied, then of course we can conclude that f is a contraction map. If f is a contraction map, then if you want to find the root, then if you want to find the root of the equation fx equals to x, which basically says that you want to compute a fixed point, then you can perform this iterative scheme. You can start off with some x0, you set x1 is equal to f of x0, and you can set f of xn is equal to, sorry, uh, you can set xn plus 1 to be equal to f of xn and so on. This will converge to the fixed point. Okay, so let's solve this problem uh, based on this understanding. Okay, so your equation over here is x cubed minus 7x plus 2 is equal to 0. And you want to somehow, this is your f of x, you somehow want to change this to a form some x is equal to g of x, where this g is a contraction mapping. Now, of course, notice that uh, now, of course, notice that uh, you can, of course, write this equation in many ways, but it's not necessary that all of them would be a contraction map. Okay, if uh, if if it is not a contraction map, then the fixed point iteration scheme, which is basically this scheme, this is the fixed point iteration scheme. Then the fixed point iteration scheme will not work if it is uh, if it is not a contraction mapping. Okay, so in particular, um, let us evaluate these examples. Okay, so the first is that they've written this x uh, to be equal to 7x plus 2 to the power one third. So this is our g of x. Okay. Now the question is g of x a contraction map? So let us see what is g dash of x. So if you compute g prime g dash of x, that is equal to one third uh, 7x plus 2 to the power minus 2 third times 7. Okay. Um, right. So now what is g dash of x? G dash of x, you're evaluating g dash of x within the interval 0 comma 1. So in the interval 0 comma 1, if x is equal to if x is equal to either 0 or 1, you can just put the values over here. Uh, you will notice that this quantity g dash x, so at x equals to 0. Um, okay, sorry, maybe at x equals to 1, we should check this. So this is uh, so this g dash 1 is equal to one third. Um, 9 to the power minus 2 by 3 times 7. If we evaluate this quantity, this is greater than 1. Okay. In general, uh, g dash x mod is greater than 1. So if this g dash x uh, uh, mod is greater than 1, then you are guaranteed that this will never converge to the fixed point. Okay. Uh, well, I mean, uh, well, uh, you can't just conclude whether it's going to it's definitely going to diverge from the fixed point. That may be difficult to answer, because uh, in order to do that, if it is possible to, um, yeah, sorry, I take back my words. Yes, it will. So let me just write it down. If this g dash of x is uh, is greater than 1, then it will diverge from the fixed point. So if you pick a iteration scheme which is this will not converge to the root. Okay. Similarly, let's look at the next formulation, which is the C, which is x is equal to x cube minus 6x plus 2. So this is your gx. So again, if you compute g dash x over here, which is g dash x is 3x squared minus 6, you will notice over here that this g dash x is also greater than 1. Okay, so this iteration scheme will also fail because these are not contraction mappings. And not only are these not contraction mappings, what is happening is that the gaps between 2 points. So essentially, why will this fail? This will fail because um, if you take the difference between xn plus 1 and xn, that is equal to f of xn minus f of xn minus 1. Well, this in turn is equal to some f dash of some theta, let's call that theta n, times xn minus xn minus 1. Okay, but this f dash theta n is greater than 1. So this quantity is actually greater than xn minus xn minus 1. So the progressive, so the sequence that you are computing, so the sequence is actually not a convergence sequence. It's in fact a divergence sequence. Um, because these numbers are going to get bigger and bigger actually. Um, and so if this g dash x is greater than 1, you will never converge to the fixed point. So eventually, if you let's say if you look at this option where gx is equal to uh, x squared plus 2 by 7, and if you compute g dash x, then this g dash x is equal to 2x by 7, and g dash x is less than 1. So this is the iteration scheme which will converge because uh, because under this formulation it becomes a contraction map. Okay, so I hope this is clear. The idea is that when you given an equation, you express the equation as a fixed point problem, but but there may be many ways to express the equation as a fixed point problem. So all these A, B, and C are all fixed point formulations. But if you have any such fixed point formulation, it's not guaranteed that this particular iteration scheme will succeed. So we are interested in this particular iteration scheme. We do not have a guarantee that this particular iteration scheme will succeed unless we can ensure that it's a contraction map. Okay. So yeah. So I hope this is clear. If you have any questions, you can ask me. Otherwise, we'll move on. Okay. So let's say so let's look at one problem along these lines, which is this problem. So again, you might notice that there are many ways to set up a fixed point scheme. But if you choose this, uh, the fixed point scheme this, so if you choose x to be equal to, okay, let's see. So we have 10 times x minus 1 is equal to sine of x. Now, if you choose this x to be equal to sine x by 10 plus 1, you do not necessarily have a contraction map. So if you choose gx to be equal to sine x by 10 plus 1, then your g dash x is equal to, well, yeah, sorry. Your g dash x is equal to cos x by 10. And yeah, sorry. And g dash x norm is less than 1 because cos x is always smaller than 1, smaller than or equal to 1. So yeah, so this formulation would work fine, and you can then use a fixed point iteration scheme. Uh, yeah, with an initial guess, they've asked you to set x naught to be equal to 1. You can complete the calculation. Okay. Just give me 1 second. I'm looking up the problem. Okay. So now we look at finding solutions to systems of equations. Starting off with this one, which is the Gauss-Seidel equation. Okay. So if you have a system of equations, I hope you understand that you can write any system of equations in this compact form, right? So, for example, if you have a system of equations which is of the form some summation of a I j xj for j equals to 1 to n is equal to bi, and I itself varies from 1 to up to n. If you have a system of equations like this, you can, of course, write the system of equations of the form ax equals to b, where this A is this matrix where aij is equal to the coefficients aij. Okay. Now, if the solution exists, okay, um, which is always guaranteed to exist, so a sufficient condition that a solution always exists is that this matrix A is an invertible matrix. If the matrix is not an invertible matrix, then the solution may not exist. And if the solution exists, the solution would not be unique. Okay. But assume for now that this matrix A um, is in fact an invertible matrix, then your solution is basically equal to A inverse of B. Okay, so we actually have a closed form representation of the solution. So now we may ask that if we have a closed form representation of the solution, why must we perform an iterative scheme to compute a solution? Like why would I compute uh, why would I compute an approximate solution to the solution to the system of equations if I can just compute a closed form representation like this? And that's a fair question. So the reason is basically this, that in practice, when you are solving systems of linear equations, you do not get systems of equations in 2, 3, 4 variables. You can get systems of equations in 50 variables, 100 variables, and so on. So then what happens is that the matrices that you are dealing with are no longer like 2 cross 2 or 3 cross 3 matrices. They could be like a 1,000 cross 1,000 matrix. And when you have a 1,000 cross 1,000 matrix, then computing the inverse. So you, of course, using a computer to computing these inverses and so on. But uh, but setting up a program that computes the inverse of the matrix, which is like let's say a 1,000 cross 1,000 matrix, is going to be a very it's a computationally expensive process. Okay, and so in practice, when you have these systems of linear equations, like for instance, any linear algebra solver that you may have used in your engineering program, which can solve a system of linear equations. These linear algebra solvers actually almost never compute the inverse of the matrix. They actually always use some kind of an iteration scheme to compute the solution. So here we're going to look at one such iteration scheme. This is called the Gauss-Seidel method, and so the Gauss-Seidel method is basically this. Let's say you have a system of equations of this form: Aij xj is equal to bi. Uh, then what you do is um, for each I, so you have n equations and n variables. So j is from 1 to n, and I is from 1 to n itself. So for each I, you write this, you basically do like a transposition. You write xi is equal to bi minus sum over of aij xj, where j is from 1 to n, but j is not equal to I. Okay. Uh, minus divided by aii. Okay. Now, of course, for this to work, you need these AIIs to be not equal to 0. So this method works only when the if you write this coefficient matrix as A, then the diagonal elements of this coefficient matrix must not be 0. Okay. So now having set up so having like rewritten the equations in this way, you set up the iteration scheme as follows. So let's say you have some initial guess. Let's say x0. This is let's say your initial guess. Then the next step of the iteration is basically this. You write x1 to be equal to, sorry, not x1. Yeah, sorry, x1 1. Okay. A1j xj0. where of course j is not equal to I, j is not equal to one by a11. Right. But the next term, which is x2 in the first iteration scheme, so x2 is of the form some b2 minus sum over of a to j xj, where j is not equal to uh, where j is not equal to 2 upon a to 2. But in this formula, uh, so if we just write this down, what this is equal to b2 minus a to 1 x x1 minus a to 3 x3 and so on divided by a to 2. But the idea is that when you are substituting for this x1, you don't actually put x0, you actually put x1. So once you have an estimate of x1, you, instead of putting x0 the way we put it over here, we'll actually put x1 over here. X1 with the first estimate. But x3s, x4s, and the rest of the terms, we continue to use the 0th estimate. Okay. In the third term, which is, let's say, x3, so x31 is equal to b3 minus. So now you know x11 and x21. So that's what we're going to plug in. It will be equal to a31 x11 minus a32 x x21. But the rest of the terms will continue to have the 0th estimate only. So that will be a34 x40 and so on by a33. So basically, the idea is that once you get the first estimate of x1, in the when you're estimating for the second variable x2, you use that in the equation. Once you know x1 and x2, you use that for the third one, and so on. So it's actually pretty simple. If you let's solve this, uh, should be pretty simple. So, sorry. So if you write the system, so x is equal to 28 minus 5y minus 3z. The next term is y is equal to 76 minus 3x minus 13z by 7, and z is equal to 1 minus 12x minus 3y by minus 5. Okay. So if my guess is some xn, yn, zn, then I update my scheme as follows. I set xn plus 1 to be equal to 28 minus 5yn minus 3zn. I set yn plus 1 to be equal to 76 minus 3x n plus 1. I'm no longer putting n over here, I'm putting n plus 1 because I've computed n plus 1 here already. Minus 13 z, but z I'm going to use n only because I do not know zn plus 1 yet. By 7, and zn plus 1 is equal to minus 1 minus 12 xn plus 1 minus 3yn plus 1 by 5. Okay, so this is my iteration scheme, and starting off with um, any iteration 101. If I perform 6 iterations, I'll arrive at the answer. Okay, so I hope this is clear. Pretty straightforward. I'm not going to discuss things like the convergence of this method and why this works and so on. It's already I don't think it's part of this link. Okay. Um. Well, okay. What else? Okay, let's look at this thing. This is a simple equation only. This is a simple system. It's called the Gauss elimination. It's basically it's kind of reducing it to a row major form. Um, so some linear algebra here. Uh, okay. So the Gauss elimination method is not an iterative scheme. Okay. It is in fact a scheme where you can actually get uh, the exact answer. Okay. So the idea is basically like this: if you are given a if you are given a system of equations which is of the form some ux is equal to b, where u is an upper triangular matrix. Okay. So what this means is that the system of equations looks something like this: um, u11 x1 up to u n n x n is equal to b1. The second equation, in the second equation, the x1's coefficient is actually 0. So it's actually u22 x2 plus u2n xn is equal to b2. Similarly, in the kth equation, uh, all the coefficients of the variables x1 to xk minus 1 are 0. And finally, in the last equation is of the form some u n n x n is equal to bn. So if you have a system of equations which looks like this, then it is very easy to solve it, right? Because all you have to do is you first solve for xn minus 1. So you do this sort of back substitution. So you set xn is equal to bn by unn. Then you substitute the value of xn in the previous equation. So the previous equation would look like un minus 1, um, un minus 1, n minus 1, xn minus 1 plus un minus 1, n xn is equal to bn minus 1. So once you know the value of xn, you can substitute the value of xn over here, and you can get xn minus 1 accordingly. So essentially, what happens is that if your system of equations is of this kind, which means that if U is an upper triangular matrix, then it is particularly easy to solve this system of equations. Okay, and the Gauss elimination method is basically that it gives you a method where if you have a system of equations, you can reduce the system of equations to another system of equations, an equivalent system of equations, where the coefficient matrix is an upper triangular matrix. So the way this is carried out is actually quite straightforward. Um, let's say you are given you're given any such matrix A, uh, which is you have these entries of the matrix. What you do is that like whatever the coefficient of x is, so let's say the coefficient of x1 is in the first equation is a11. So if you take an example, that would be like um, let's say you have a system where the equation is a11 x1 up to a1n xn is equal to b1. For all other equations, what you do is that you do this basically. Um, for the kth equation, the k is of course greater than 1. So if you write this as equal to 1, and if you write the kth equation as k, then you get an alternative system where the you replace the kth equation with a new equation, which is where this new equation is basically uh, where this is equal to k minus uh, ak1 by a11 of the first equation. So these are equations basically. So when you do this, what happens is that the coefficient of x1 in the kth equation now becomes 0. Okay, so let's solve this here. This will be very easy to do. So you have 5x minus, just 1 second. So if you write this system of equations, uh, you can write it in this way: 5 minus 3, 3, 2 minus 1 minus 7 minus 3, 9, 1. And what you can do is the right hand side, you can write it in this way: minus 1, 3. Okay. Now, the idea is to turn this into an upper triangular matrix. And what you're essentially doing is that you first want uh, this term to drop to 0. So in order to make this term drop to 0, what you do is that you do row 2, you set the second row to be equal to row 2 minus um, 2 by 5 times the first row. Okay. If you do that, then what happens is you have 5 minus 3, 3 minus 1, but this term is now equal to 0. What about this term? Well, you can just solve that now. So, I mean, essentially what you get is 2 minus 1 minus 7. This was your first row minus 2 by 5 times the first row. 5 minus 3, 3. So this is equal to 0 um, minus 1 plus 6 by 5. Here this is equal to minus 7 minus 6 by 5. Okay. And of course, you have to change the right hand side also. The right hand side becomes here minus 1 minus 2 by 5 times, sorry. The right hand side becomes 3 minus 2 by 5 times minus 1, which is 3 plus 2 by 5. Okay. So when you do that computation over here, whatever the entries are over here, you'll get a new entry over here. But this term is now equal to 0. Similarly, you modify the third row as well. You set this third row to be equal to the third row minus 2 by 5, plus 3 by 5 times, plus 3 by 5 times the first row. So when you do that, this term also becomes 0 and you get some entries over here. These could be some non-zero entries. Now, once you have the system in this particular form, what you do is that you repeat the same process for this submatrix. You repeat for the smaller submatrix. And once you do that, you will eventually get a form where uh, where the entire matrix over here would be an upper triangular matrix, and here you're going to have some entries over here. So once you've reduced it to the upper triangular matrix, your system of equations now looks like this. So once your system of equations looks like this, you can then easily apply a substitution and get the values. So this is called the Gauss elimination. Okay, and what you are also allowed to do is that you are also allowed to interchange two rows. Okay, so in other words, say when you are uh, when you are dealing with this particular block matrix, let's say this is just for example's sake, you see that the that this particular term over here is 0. So if this term over here is 0, then of course you can no longer do this because you'll have a division by 0 error. So then what you can do is uh, you check the you check the uh, you can check any of the rows, and whichever row has a non-zero element over here, you can swap you can interchange those two rows. Okay, so in other words, let's say your submatrix looks like something like this. Let's say it looks like 0 uh, and then some numbers, and but this quantity has, let's say, 1 and then some numbers. You can interchange this with this. So you can interchange row 2 and row 3. You can swap them. Okay, this is something you can do so that you do not get the division. I mean, you need the diagonal terms to be non-zero once you perform this scheme basically. So if something is equal to zero, you are allowed to you can interchange two rows. Okay. Um, all right. So I hope this is clear. Uh, we are now going to look at some numerical methods for solving integrals. So we are done with systems of linear equations. We are done with finding roots of equations. We're going to now look at um, some numerical methods for solving integrals. Um, yeah, I mean these things um, are mostly quite formulaic. So you'll have to remember these formulas over here. So let me just write over here. The first is the trapezoidal rule. And for the trapezoidal rule, the idea is basically like this. This is the most intuitive idea that if we have an equation, sorry, um, that if you have some function f of x, um, and we want to compute the integral between uh, from the interval a to b, the idea is that you sort of chop uh, this the interval a into some number of pieces. Um, let's say you have divided this interval into some number of pieces over here, and let's say you call this piece as some yk, and this will be equal to some yk plus one. So then you kind of estimate the area as a sum of the areas of the trapezoids. Uh, so if you have like this, you kind of consider a trapezoid like this, and you basically take the area of this trapezoid. So the area of the trapezoid is basically if this is yk and this is yk plus 1. And let's say you have chosen these gaps to be equal to some age. Uh, so your y0 is equal to, let's say, a, your yn is equal to b, and you have kind of partitioned it into these small subintervals where yk plus 1 minus yk is equal to h, where h is basically your partition length. And the smaller the value of h, the more better approximation of the integral you will get. In fact, this is like like uh, whatever the integral is as a Riemann sum. This is just a discretization. This is just the Riemann sum, but not taking the limits over a finite value of each. Basically, over a non-zero value of each. And so the area of this trapezoid is equal to half times uh, yk plus yk plus 1 plus h times h. So when you sum it up, so when you write this integral as uh, as a sum of the trapezoids, which is the iteration that you are going to use over here, then it follows that uh, in a very straightforward way that uh, the integral I, and you, because you're using an estimate h, so let's write h over here, is equal to this particular form. Okay. So yeah, it's pretty straightforward over here. Um, let's solve one problem. Okay. As we said that um, the smaller the size of h, uh, the uh, the uh, the yeah, in other words, the smaller the size of h, the greater is the closeness to the original value. So here the question is like how small should you make your h so that so smaller the number of h, more is the number of subintervals, so that you incur a small total error of less than 10 to the power minus 4. So for the trapezoidal rule, we have the following error estimate. It's important to remember this. This is the error estimate. So for the trapezoidal rule, the error estimate E is given by P minus A by 12 times H squared M. Okay, and what is this M? So the M is basically the max value m is basically the max value of uh, of this integrand. Okay, so we're going to use this formula to determine the error term over here. So the error term is 10 to the power minus 4, and m over here. So if you write f double dash x, so then f double dash x is equal to my is equal to 2 by x plus 4 cube, so that you get m to be equal to 1 by 32. So in order to incur an error of less than 10 to the power minus 4, you if you plug this over here, you get so b minus a is 2, so it's 2 times 12 times h squared times 1 by 32. So if you compute this, you need to compute this quantity. You will get h squared to be greater than sorry, yeah, you will get this h. Actually, sorry, I'm making a mistake. Just give me 1 second. Uh, mm, okay, okay, okay. Yeah, sorry. Uh, right. So the error term is 10 raised to the power minus 4. So if we set b minus a by 12 times h squared m to be less than 10 to the power minus 4, then that is a sufficient condition that the error term is um, that the error term uh, is going to satisfy this condition. So if you do that, you will it's actually not less than, it's actually greater than equal to. You will see this h squared term uh, can be at most as big as whatever this quantity over here is, which is uh, 10 to the power minus 4 times 6 times 32. And you can solve for this and get a particular value of each. So whatever the value of h is, you can then subdivide the interval into that many divisions, basically. So in other words, whatever this h is, your n was basically going to be equal to this b minus a by h. Okay, so I hope this is clear. Um, if you're interested in seeing a proof of how we arrive at these error estimates, then you can then maybe you can reach out to me. I can share with you a proof of how we arrive at these error estimates. But it's a bit difficult to talk about all of these within the given frame of time because there are many things to be covered in one particular week. So it's a bit difficult to go into the details of each of these. And finally, there's one more. Uh, Right. There's finally one more scheme, which is called the Simpsons rule. I'm just going to write it down over here. I'm not going to go into the proof of how we get this. Um, so this is the called the Simpsons 1/3 rule. Yeah. So I think the way this Simpsons 1/3 rule works is that it is better than the trapezoidal rule. The trapezoidal rule is, as you can check over here, the trapezoidal rule is like a first order estimation. Okay. Uh, uh, it's a first order estimation because the trapezoid that you're considering over here, this trapezoid is uh, right. I think this trapezoid is basically like a second, which connects the 2 points of this curve, and um, yeah, um, right. So and what this does is that it this is the first order approximation because um, the second over here is going to be equal to the tangent to some point that lies within uh, this interval, right? That's just the mean value theorem. The Simpson's rule, on the other hand, is a higher order is a higher order approximation. I think you take not just the um, you take not just uh, you take not just the, the first order approximation, but also uh, the second order approximation. I think that's how you arrive at but I'm not sure exactly. You'll have to check that. But anyway, for the purposes of your problem, you have to remember this formula. The idea is once again that you choose some subinterval length h, and then you subdivide it, and this is the formula you use to compute the integral. Okay. So I hope it's things are clear more or less. If you have any questions, you can ask me. We've gone beyond time today. There's so many things to cover.